Thank you very much for the invitation. So it's still in progress. I didn't finish the preprint, and it was suggested during my PhD thesis by Loïc Merel. So I'm going to state results about this conjecture of Mazur-Tate and apply them using the theory of the Eisenstein ideal to supersingular elliptic curves. So let me recall a little the setting of the conjecture of Mazur-Tate. So first the p-adic analog. So let E be, Q be an elliptic curve. Say a conductor N. So we know that E is modular. So there is an associated modular form. Yeah. And so from that you can associate to E several objects. So you have like the modular symbols attached to it. So let's denote them by phi E plus and phi E minus. So for the complex conjugation, I will recall that soon. You also have the complex L function. And if P is a prime for which E has ordinary reduction, meaning good ordinary or split multiplicative, you have the p-adic L function. So here S in C, here S in ZP. And so Mazur-Tate and Tate-Albom formulated p-adic analogs of BSD conjecture. In the case where E has split multiplicative reduction at P. So yeah. So then in this case, what happens is that the p-adic L function has a trivial 0. So then L of LP of E1 equals 0 for because there is some Euler factor which is like 0 by definition. So in this case, there is the so-called p-adic L-invariant. Which is attached, it's a purely local number in QP, which is attached to E via the p-adic uniformization. And you have the formula, the derivative at s equals 1 of the p-adic L function is the L-invariance times the classical value. And you have to normalize it through some period. So I will recall all these objects in a moment. But the thing is, so this conjecture was proved by Greenberg-Stevens, and and so Mazur-Tate they've stated analog conjectures at finite level, which does not involve like a p-adic limit, and it was proved in some cases by de Chalit. And in this talk I'm going to give some more results about it. So what I'm going to do, I'm going to recall more precisely what this equality means, and then recall the Mazur-Tate conjecture and state what we know about it. So let me talk about modular symbols. So let M gamma naught of N be the set of gamma naught and equivariant homomorphism from the degree 0 divisor on P1Q to C. And so this space is a C vector space, but there is a natural action of the Hecke algebra in it. So T is a Hecke algebra. So acting on the space of weight 2 modular form of level gamma naught of N. So this includes the Eisenstein series. So you also have an action of the complex conjugation on it. So yeah. So let me recall briefly what this action is. So let's see, denote the complex conjugation. Then if you have a phi in m gamma naught of n, like c times phi evaluated in a divisor x minus y, just phi of minus x minus y. Yeah, this is the definition. And so what is interesting is that you can relate these modular symbols to modular forms. So you have a map from m gamma naught of n to like, no, in the other way. So to each cusp form, you can associate a modular symbols. So to f, you associate like the map to which sends a divisor like that to the integration between x and y of f of z dz. Yeah. So you take the integral along a geodesic path. So you can only do that in like for cusp form, but you could like in some cases include Eisenstein series into this picture. And so if E is an elliptic curve, so you can define like phi E plus to be like phi E like plus. Maybe let's denote by a bar the complex conjugation. So C of phi, we denote it by phi bar. So omega E plus and omega E minus are canonical real elements, which are the Néron period. So in general, if you work with a modular form, you don't have quite canonical periods. So the resulting modular symbols are only defined up to a scalar. And so using these modular symbols, you can define the p-adic function. So in fact, only this one is important for us. The minus one we will never use. So LP ES is constructed using this plus modular symbol. Okay. So now if P is such that E has multiplicative reduction, then I was talking about the L-invariant, so I'm going to define it quickly. So in this case, E is a Tate curve. So like P bar star. So you can uniformize it like that with some QE and QP star. So this is a Galois covariant isomorphism in particular. And so the L invariant is defined to be the p-adic logarithm of QE over the p-adic valuation of QE. So the number in QP. So here you have to choose a logarithm. We choose the one such that log P of P is 0. Called the Iwasawa p-adic log. So yes, now I defined everything. I somehow defined the p-adic function. I defined the L invariant, and so you have this formula. But let me restate this formula without involving p-adic functions, using just modular symbols. So the formula LP E1 prime equals LPE times LE1 omega E plus is equivalent to the congruence that for all n greater or equal to 1, we have the following congruence: the sum for a equals 1 to p to the power n minus 1, and a is prime to p, of the modular symbols evaluated in a over p power n minus infinity times the p-adic log of a is so LPE times the special value at s equal 1 modulo p to the power n. So if you unravel the definition of the p-adical function as a distribution, you get like this family of congruences for all n. If you take the limit, you get this equality. So maybe it's not really well defined because this is only a rational number. Yeah, I didn't say it, but this phi e plus and phi e minus, they take value in Q, not only in C. So there may be some denominators, but you clear them out, and then you have this congruence. So the idea of Mazur and Tate was to exponentiate this formula to get something a little more refined. Yeah, before I go on to Mazur and Tate, let me just say the idea is that we are used to prove that. So idea of the proof. So this is due of course to Greenberg and Stevens in the 90s. So there are two main ideas. The first one is to put your elliptic curve into a Hida family and to use a two-variable p-adical function. There is a parameter k, the weight, and a parameter s. So use two variables, a p-adical function, LP of the weight and s. And so using that and the functional equation, you can relate what? The derivative of the p-adical function to like AP prime. So this is the derivative of the Fourier coefficient of E in the Hida family. The second main idea is to use it's a Galois deformation of the Galois representation attached to E. So use the Hida deformation of the representation attached to the elliptic curve. And so using class field theory, Kummer theory mainly, you can relate so AP prime to LP. Okay, these are the two main ideas. So now I will talk about the Mazur-Tate conjecture and explain a little what are the tame analogs of these two ideas. So you put your elliptic curve, or the modular form attached to elliptic curve, into a Hida family. So this depends on the weight. And so you have AP of the parameter k, and you derive it at k equals 2. So this is AP prime of 2. It's an analytic function of k. But so in some sense, in the Mazur-Tate case, it's much more elementary. You don't have to actually compute actual derivatives or actual p-adic things. Yeah, maybe. Okay, so Mazur and Tate just took this formula and exponentiated. You just take the product of A over phi E plus A over P minus infinity congruent, or over n if you want, congruent to QE per so a equals 1 to p to n minus 1, and n is prime to p, IA is prime to p. But in fact, only n equals 1 is interesting. Only this case adds new information. So again, maybe you have some problems because this may have denominators, but you have to multiply by the denominators to get a formula which makes sense. And so I think this conjecture is still not proved, as far as I know. But I'm going to state partial results about it. So let me briefly state a little more conceptual conjecture. This is a little ad hoc. It uses an analog of the p-adic function, which is called modular elements. So in fact, if you have any integer m, you can define the modular element attached to your elliptic curve, which is just the sum of phi plus of a over m minus infinity times the element a. So a is in z mod mz star mod plus or minus 1 because this is the even modular symbol. So this lives in q bracket then mod mz star mod plus or minus 1. So this is really like the tame analog of the L function.
You identify CL and what's the last bit?
What one?
I can't read it.
Can I read it? It's phi e plus of a over m minus infinity times the group ring element a. So this lives in Q. This has coefficients in Q, but in fact, this has coefficient in the ring R, where R is almost Z, except you have to invert a little thing. So R, you can take it to be Z, and you invert the order of the cuspidal subgroup of X0 of n, where n is the conductor. Also, you have to invert the Manin constant. But let's not care a lot about that. And so, why is this element somehow related to the p-adic L function? Well, if you take m equals p to the power n and you take the projective limit of this element, you get essentially the p-adic L function. But the point is you can do it for any m, not just the power of p. So let me just recall the interpolation formula, which is a nice exercise. So what is the formula? If you have any Dirichlet character from Z mod mz star, even character, yeah, and primitive, and then you apply chi to this element. So you apply chi to that. You get essentially the twisted L value at s equal 1. So you get, there is a Gauss sum. Okay, so this is why this is really something related to the L function. And so let me just restate this congruence of Mazur-Tate in terms of augmentation ideals. So let J be the augmentation ideal of the group ring. So to say that the L function vanishes at some order R means that the theta element is in the R power of J. And then you can ask what is the Taylor coefficient, the leading Taylor coefficient. So conjecture is that theta E M is in J power the rank of the model Weil group plus the number of prime L dividing M for which E has split multiplicative reduction. So this is like the analog of the BSD conjecture, except you have some extra vanishing, which is like the analog of the exceptional zero. And so if M equals P, then we can make we can reformulate the Mazur-Tate conjecture. So it's equivalent to the following. So you take the image of theta E P in J mod J square. So this is somehow the analog of the derivative of the p-adic function. This is so the L invariant, like QE. You reduce it mod P times phi E plus of 0 minus infinity, which is the analog of the special value at s equal 1.
So what is the rho? You say M equals rho. What is rho?
P. Yeah, it's not rho, it's P. Okay, so now this conjecture was proved if the conductor of the elliptic curve is prime under some assumptions by Ehud de Chalit. Yeah. So here is the theorem. It was proved by de Chalit in the late 90s. So if the conductor of E is P, then Mazur-Tate conjecture is true. If some technical assumptions hold. So if there exists a modular parametrization from x naught of P to E, which has degree prime to which has degree prime to L. Sorry, I didn't tell you. What is L. So it is the L part of the Mazur-Tate conjecture, which is true. So L is a prime dividing P minus 1. So you take such prime, and so Mazur-Tate conjecture is an equality in Fp star, and you just tensor it with ZL. And this is true if this assumption holds. So you will see why we need this assumption. It's because de Chalit proves something much more general than this, but at the level of the full modular curve, not just at the level of the elliptic curve.
So there is an L.
So you fix a L which divides P minus 1, which is greater or equal to 5. This is also an assumption. And you assume that, and then Mazur-Tate holds tensor the L.
Your conjecture has nothing to do with L, right?
Yes. So the conjecture of Mazur-Tate is something in Fp star. you take L equals 1. Some equality mod P. And you just tensor that with ZL. It's like when you want to prove BSD, you do it prime by prime.
I mean for all L.
For all L greater or equal to 5, which satisfies this. So yeah, the Shalit was not able to include L equals 2 and L equals 3. Okay, so what the Shalit does, and what I'm going to improve, so the theorem of the Shalit is partial, and I'm going to improve it a little. Or more precisely, it proves Mazur-Tate conjecture for the Jacobian of x naught of p. So it's the analog of Mazur-Tate conjecture for the Jacobian of x naught of p. Because Mazur-Tate conjecture can be stated, in fact, for any abelian variety, and in particular for this one. So how does it work? So we need, so the important thing was the p-adic uniformization of your elliptic curve, because E was assumed to be split multiplicative reduction, and so you had this state curve uniformization. So you need to do the same thing with this Jacobian. And this is possible due to results of Mumford, because x naught of p, there is a model due to the linear and Rapoport over Zp. There is a model such that the spatial fiber is a copy of two p1s which intersect transversally. Like it's two copies, sorry. So it intersects at the supersingular points. So yeah, maybe you should work with the quadratic extension of FP, because the supersingular points are not defined always over FP. But let's ignore these technical things. So in this case, let's denote this point by S. So S is a set of isomorphism classes of elliptic curve or supersingular elliptic curve over FP bar. So this is a finite set which injects into FP square via the L-invariant. And so you can look at the character group of the spatial fiber, which is like the free module over this set. So let X be the free module over S, and X naught be the augmentation subgroup, set of degree 0 elements. So the fact is that there exists a pairing Q from X naught to X naught to QP star, which is, so it's a bilinear pairing. And this bilinear pairing is going to give you the analytic uniformization of x naught of p. So be careful, here it's a multiplicative group. So it's a little strange to work with additive and multiplicative group, but that's life. So okay, this pairing induces a map where x naught to its dual And associated to this map, you get an analytic uniformization of the Jacobian of x naught. So this is an analog of the Tate curve. So there is a Galois QP bar over QP, equivariant isomorphism from J naught of QP bar to the dual of x naught to QP bar star modulo the image of Q of x naught. So this is a lattice inside this group. So this is really the analog of Tate curve. Here it's like the QE, this is like QP bar star, but it's a one-dimensional case. And so now that we have this, we can formulate the Mazur-Tate conjecture for J naught. So J for P, sorry. So what you need to do is the following. So first you choose, so let L be a prime like in this statement here. You just assume it's greater or equal to 5. There is no elliptic curve anymore in the picture. So what you have is the following. You have the p-adic valuation modulo L. So it's a p-adic valuation modulo L. This is like the analog of the p-adic valuation in the Mazur-Tate conjecture. And you have the discrete logarithm QP star to Z mod LZ. So you fix such a discrete logarithm. So how is it defined? You first project to ZP star, then you project, you reduce mod P, and then you choose some map here. So you just fix such a group homomorphism. Group homomorphism. And so now you want to define the analog of the L-invariant. So you have to take essentially the log of Q modulo the valuation of Q. So you need that the valuation of Q is invertible. And this is true, in fact. So so the fact is that the composition, the valuation composed with the map Q, little q. So this is a map from X tensor Z mod LZ to sorry, X naught to homomorphism of X naught or Z mod LZ. So the fact is this map is an isomorphism. It's essentially like the Kronecker pairing between X naught and itself. And so what you can do, you can define R to be VL composed with Q inverse, composed with the logarithm. So this is something which goes from, this is something which lives in the endomorphism of X times Z mod LZ. And so, so this endomorphism, so X naught, sorry, happens to be a Hecke operator. So fact L is a Hecke operator. So let me, I have something more to say. So L here is just an endomorphism of the augmentation subgroup. So it is something really in the cuspidal ecoalgebra. But there is something very interesting. This pairing can be extended to a pairing from X times X to QP star. So it's very non-trivial, but you can extend it. First, you extend it from X naught times X. And the interpretation is that it uniformizes the generalized Jacobian with respect to the cuspidal modulus. And then there is something a little obscure, which allows you to further extend Q.
So Q is symmetric, right?
You can prove it's symmetric, yeah. And it's also Hecke equivariant. It's not at all obvious that it's Hecke equivariant. It amounts to some non-trivial identity for supersingular chain invariance.
I thought that's how you proved this fact.
Yeah, so this fact is true for x naught times x naught. But if you want to prove it's equivariant here, it's a little more difficult. So if you view, I can do everything by removing the 0 here. So it's really an endomorphism of the full supersingular module, and it's so the fact is that it's an Hecke operator in the full Hecke algebra. So that's going to be important because we are going to talk about Eisenstein ideals. So we really want something in the full Hecke algebra. So now I can state Mazur-Tate conjecture. So I will erase the old one and state the new one. So this time it's due to de Chalit, but also like to myself. I had to improve the Chalit result. I will tell you how. So the result is the following. You take any modular symbols of weight 2 and level gamma naught of P. So that recalls as the space of modular symbols. And then you have the following formula. So because phi is a modular symbols, you can, and L is a Hecke operator, you can act on it via L. So this is the action from this Hecke operator on phi. So this is again a modular symbol, and you evaluate it to 0 minus infinity. And the result is the sum for A equals 1 to P minus 1 of the discrete log of A times phi of A over P minus infinity modulo L. So this is an equality in Z mod LZ, or in fact Z mod L power something, but for simplicity, let's say mod L. Yeah, so this is a modular symbols with coefficients in Z mod LZ. You can talk about the space of modular symbols in any ring. Yeah, so this is the analog of the L-invariant. This is the analog of the special value at s equal 1, and this is the analog of the p-adic function. And so what de Chalit proved, he proved something like that, but only in a he proves this equality for a subspace of modular symbols, which essentially is the Eisenstein ideal times this space. So when you localize this story as Eisenstein ideal, you miss something if you apply directly de Chalit. So my contribution is to prove this formula for any modular symbol. And so again, what's the idea of the proof? It's to apply the same idea as Greenberg and Stevens. So you replace the p-adic L function, the two-variable p-adic L function, by two-variable modular elements. And you replace the HIDAF deformation by the Shimura covering. So you get a deformation from x naught of P to x naught of P. So there is a Galois representation. Here you have a small deformation with the Galois group Z over Pz star, and this deformation about the L-invariant. So this is completely similar to Greenberg-Stevens, but in some sense completely different also. It doesn't use any ordinary thing or p-adic thing. Okay, so I'm not going to give more information about the proof of that. Yeah.
Just in a general sense, what is this quadratic form Q made from? Is it an algebra geometric thing having to do with where the supersingular points are located, or what?
Yes, this has to do with the Schottky uniformization of x naught of P. So x naught of P, like over QP, this is a p-adic curve, and there is a p-adic uniformization via some group, which is a Schottky group, and modulo some kind of p-adic upper plane. And from that, you can construct Q.
Okay.
it's constructed with theta functions, like in the classical case. But the point is, you don't really need the actual definition. You only need this.
J naught of P, that's the Jacobian of X naught?
Yeah, sorry. J naught of P, the Jacobian, X naught of P. So yes, about that I have something to say. So yeah, a priori we don't know anything about this, right? It's some abstract pairing. But in fact there is a formula for it, modulo the principal unit. It's also due to de Chalit. Yeah. It was conjectured by Osterley and then proved by de Chalit. So what is the formula? So this is a quite deep result of de Chalit. So for any elliptic curve, supersingular elliptic curve in S, you can apply the L-invariant, which we just defined here, to the element E in X. So this is an element in X, which is given by the following formula. So this is a sum for all E prime in S, which E prime not isomorphic to E, of the log. How does it work? Of the J invariant of E prime minus the J invariant of E times the element E prime minus E.
Sorry, what's the notation on the left?
Here?
Yeah.
So L is a EQ operator, so it acts on the supersingular module X. In fact, it's by very definition, it is an endomorphism of the mod L supersingular module. So you can apply it to any element of it, and you get this linear combination. So here, so these are the J invariants of the supersingular elliptic curve, and you apply log to that. So you get an equality in Z mod LZ bracket S. Yeah. And so now I think I described what I wanted to describe about the Mazur-Tate conjecture, and I'm going to give some applications to supersingular elliptic curves.
Can you just tell us vaguely how this is proved?
Which one? This one?
Yes.
This is very complicated. So you have to make a fundamental domain for, here, choose a good fundamental domain, and then do computation with theta series. Because you have to really look into the very definition of Q as the product of theta series.
And why did Osterley conjecture?
This is Osterley conjecture.
Yeah, well, how did he conjecture it without doing this computation?
That I don't know. But it should be true more generally. Like I proved an analog version when you replace J by the lambda invariant. But you could do it for other opt module. But yes, the proof is somewhat. How much time do I have? 15 minutes? Okay. So now we are going to combine the two theorems, namely this one and this one. So what do we know? We know some information about L, about the action of L on modular symbols. And on the other end, we know some information about the action of L on supersingular elliptic curves. And so if we combine these two using the Eisenstein ideal, we get something. So let me recall briefly some things about the Eisenstein ideal. So this is an ideal of the full Echo algebra, which I recall acts on the space of modular form. So inside you have the cusp forms, and so you have a projection here. You restrict the action onto the cusp form, and this is a cuspidal Echo algebra, and you have a projection from the cuspidal Eisenstein ideal. And what Mazur proved is that T mod I naught, T naught mod I naught, is essentially Z mod n minus 1Z. Sorry, I'm used to use n, so it's p over 12. It's the numerator of this. So what this says is that there are some congruencies between cusp forms and Eisenstein series modulo L if and only if L divides this number. So L prime, L divides p minus 1 over 12, equivalent to exist congruencies between Eisenstein series and cusp form. There is a unique Eisenstein series in this case. Okay, and so now what I'm going to ask is, okay, L is a Echo operator. So we know that L is in mod L. This is an Echo operator modulo L. And we are going to ask in which power of the Eisenstein ideal does L belong. Yeah.
Sorry, I don't quite understand.
Yeah.
This Mazur result, because there's no P in the setup.
Yeah, P is the level of the modular curve.
Oh, I thought that's an L.
Sorry,
Sorry.
my sorry, P. It's not a rho, it's not a L, it's only a P.
What if P minus 1 is not divisible by 12?
It's only the numerator of this number here. Yeah, anyway, we only L greater or equal to 5, so we are going to ignore the subtleties at P equals 3. But yeah, the L here should be the same L as here, of course. So the question is, I don't want to erase that. Okay. Okay, L is in T mod L. And the question is, for which integer n do we have L in the Eisenstein ideals time T times Z mod LZ? So in fact, so to answer this kind of question, you need to have some information about L. And the information we're going to use is here. So using this and some of the theory of the Eisenstein, so using like the Measure-Tate conjecture. So this is this theorem. We can prove that L is in the square of the Eisenstein ideal. So this is not something very deep. You just have to look at this right-hand side and essentially see in which power of the Eisenstein ideal it lives in the space of modular symbols. And so you have tools to do that, and you find that. And so already this statement has some implications. So a corollary of that is that if you view L this time as an endomorphism of the supersingular module here, the kernel of L has dimension at least 2. So kernel of L in x times z mod Lz has dimension greater or equal to 2. So how do you deduce that from that? so you could prove it like using the formal property of the Hecke algebra localized at the Eisenstein ideal, but more explicitly, I can tell you exactly which elements are in the kernel. So there is a Eisenstein element, which is an element in the supersingular module, which is killed by the Eisenstein ideal, and there is the so-called higher Eisenstein element, which is killed by the square of the Eisenstein ideal. So more precisely, KL contains two elements which are linearly independent. So this one is the so-called Eisenstein element, and this one is the higher one, which I can give a formula, but I'm not going to use that. And so now you have an explicit endomorphism which has kernel at least 2, dimension 2. And so you get a funny consequence at the level of supersingular elliptic curves. Okay, maybe I'm not going to write. So this is the formula I gave in my abstract. So it's a little like long to write it. But so elementary consequence of the fact that the dimension over FL of KL over 2 is the following. So what is the formula? Yes, I didn't write it. So, So it's the following thing. So you consider the graph. So yeah, we're going to assume for simplicity that P is congruent to 1 mod 12. It's only like for simplicity. Consider the graph whose vertices are supersingular elliptic curves, are elements of S. So the complete graph, sorry. So this is a labeled graph. And so for instance, so if S consists of 3 different elliptic curves, E0, E1, E2, sorry. No, whatever. Yeah, sorry, I'm going to consider something a little different. Yeah. Sorry. I'm going to phrase it a little differently. So let T, this is a set of trees labeled by elements of S. Okay. So for instance, if you have 3 elliptic curves, you have 3 different trees. You have this tree. You have this one. And you have this one. And to each such tree, you are going to associate a quantity to each edge. So the quantity will be the log of the difference of the J invariance. So you have the following formula. The sum for all the possible trees in T of the products for all the vertices vertex of T of the log of the difference of the J invariant in the G of Ej equals 0. So this is the formula you get. So you sum over these 3 trees, and for each tree you take the product log of the difference of the J invariance times log of the difference of the J invariance, and you do that for each of the 3 trees, and you get 0. So this is just this is something you can prove using a generalization of Kirchhoff theorem on the number of labeled tree on a set. Okay, how much time do I still have?
3 minutes.
Okay, so let me just conclude with the question. So we know that L is in the square of the Eisenstein ideal, and we want to know when is it in the cube. And this has an answer, conjecturally at least. So it's conjectural on the conjecture of Sharifi, which we just seen at the beginning of the afternoon. Yeah, let's erase that. The question. And so to answer that, I need to introduce a K-theory group. So let K be the K2 of the cyclotomic ring tensor ZL. So there is an action of the group algebra Z mod PZ star on that, or maybe with ZL coefficient. Z mod LZ. And inside that, you have the augmentation ideal. And so the theorem is that L is in the cube of the Eisenstein ideal if and only if the following quantity, sum of log A times the Steinberg product 1 minus zeta p to the power A 1 minus zeta p lives in the square of the augmentation ideal times this group K. So A is in Z mod PZ star. So this is a Steinberg symbol, which lives in this K2. And sorry, it's not a theorem. It's conditional on the conjecture of Sharifi, which I can state in 30 seconds. What is a Sharifi's conjecture? So this depends. Assume Sharifi. So this is really the tame Sharifi's conjecture, which is not like exactly what Sharifi stated, but it's very similar. So the conjecture is the following. Okay, for any prime Q different from P, for any U V in Z mod PZ star, we have the following equality in the K2. The sum of the Steinberg symbols 1 minus zeta p power AU plus CV 1 minus zeta p power BU plus DV over all the matrices A, B, C, D of determinant Q with determinant Q and with the following assumption: A is greater than D, greater or equal to 0, and B than B, and D is greater or equal than C, greater or equal to 0. So you sum over this set of matrices of determinant Q with integer coefficients with these following inequalities. You sum all these Steinberg symbols, and this should be equal to 1 minus zeta p power Q U 1 minus zeta p power QV plus
This is the statement that the map factors to the Eisenstein
yeah,
idea.
but I didn't want to involve gamma 1 or anything. So
Yes, but not the statement that it's an isomorphism.
yeah, just the Eisenstein-Sharifi's conjecture plus I think it's Q times Steinberg symbols or anything. Okay, anyway, you get some, for any prime q, you get some equality in the k group, which I think you cannot read here, but it's really related to Hecker operators and everything. And so if it's known, then we have this theorem. But I think we don't need the full power of the Sharifi's conjecture. We only need to know it modulo the square of the augmentation ideal. And I think this is proved by some student of Sharifi, Duyin Wang. So he didn't really write it in his preprint, but he really proves Sharifi's conjecture in this setting modulo the norm in this K group. So it's enough for what I need, in fact. So probably this is not conditional at all. Yeah, thank you very much.